Okay, so this is a continuation with the confidence interval, um, though we're going to do something a bit different. So let me first do a quick summary of the confidence interval. What we said previously is that if you have a population and you're interested in a certain variable, and that variable has a mean mu and a standard deviation sigma, if you take a sample out of this population of size n and you are able to calculate x bar, then x bar is your best estimate for what mu is. This is a point estimate. Then you can do something a bit more with that x bar, is that you can take this x bar and you can build around it a fence interval using the formula that we discussed previously, which is x bar. You add and you subtract a z value, and then you multiply by the standard error of the mean, which by now you know it's sigma x bar, which happens to be sigma over root square. And for this to work, we mentioned this before, the sampling distribution of the mean has to have a normal distribution. Okay? And we discussed previously that the value of z changes according to the percent confidence you want. So if you want a 90% confidence interval, value of z is going to be 16.449. If you want a 95% confidence interval, then the z value you're going to plug in is 1.96. And if you want a 99% confidence interval, the value is going to be 2.5758 if I'm not mistaken. Okay. All right. Then the thing we said later on is that if you're not provided with sigma, sigma is unknown, so you don't know what sigma is. Therefore, the formula changes to x bar, and this time you're going to add and subtract the t, and you're going to multiply that by this s, which is but from standard deviation but from the sample, over root square of n. And that s is coming from the same sample where you got your x bar. And that t has a degrees of freedom n minus 1, and it's the two-sided t. You get it from the t table. Okay? And therefore you have your confidence interval. And we talked about how to do the interpretation for the confidence interval, etc., etc. Okay, now let's build on that to talk about what if I'm interested not in a variable that is continuous like x, rather in a variable that actually has a categorical variable. So you have a population, and now your x variable is actually a categorical, and therefore it's summarized using pi. Okay, remember pi is the proportion in the population. So again, for example, it could be proportion of smokers, it could be proportion of people with a certain disease, it could be proportion with a certain political affiliation. Doesn't matter what it is. Okay, so if I take a sample from that population of size n, I would be able to estimate the proportion in my sample, and this is the number of people that have the outcome over everybody. And that would be my point estimate, my best estimation of pi using a sample. It would be a point estimate. Well, it turns out that I can use, or I can like follow the exact same rationale we did when we were doing the confidence interval for x bar. And so if you remember, x bar was confidence interval for x bar was x bar plus or minus z, and then this is multiplied by the standard error of the x bar, which was sigma over root square of n. It turns out I can do something very similar with proportion. I can take p, which is also uh, um, a point estimate, plus or minus z, and doesn't change, and then I have the standard apply by the standard error. Okay, now if you remember when we were discussing the sampling distribution of the proportion, we said that the sampling distribution of the proportion will result in a normal distribution where the mu of the proportions will be equal exactly to pi, and the standard error of the proportion will be equal to pi times 1 minus pi. You divide by n, and you take the square root of all of that. This happens if you meet the requirement of n into pi into 1 minus pi, and that product had to be greater than or equal to 5. Okay, so if I follow the same logic that I used with the x bar, then I have to multiply by the standard error of the proportion right here, which is right here. That's the value of the standard error. So theoretically speaking, I should multiply by the square root of pi times 1 minus pi, and then you have to divide by n, theoretically speaking. But I hope that you realize something by looking at this formula, that this formula requires the knowledge of pi to be able to plug it in, whereas in reality what we're doing is we are estimating pi, and therefore we do not know the value of pi. Pi is not known, and therefore we cannot use this formula. So you'd have to do something different. What do you do when you do not know the value of the parameter? Well, you use the estimate. And what is the estimate of pi? The estimate of pi is p. So what we're going to do is go back to this formula, and we're going to rewrite it so that instead of pi, we're using p. Okay. So here we go. I'm gonna use p times 1 minus p, and I divide by n, and I take the square root of all of this. Okay. So I've replaced standard error using the pi with a standard error using p, which is exactly, this is the same p right here. That's the same one. Okay, right there. This is it. Okay. Now, the follow-up question should be then, should I replace z with the t? And the answer is no. You do not do that. Reason is there's only so even when you're calculating the standard error, you're using still the same one estimate, and therefore you're stuck with only one estimate. And long story short, the formula does not require you flipping from z to t. You keep your z. The last part of what you should do is, okay, what about this requirement right here? Well, again, in this requirement, it requires the knowledge of pi, and since we are estimating pi, we do not know the value of pi. Well, we're going to do the exact same thing we did here. So you're going to take n, you're going to multiply it by p, and then you're going to multiply it by 1 minus p, and then if that is greater than or equal to 5, then you can say, okay, requirement met, I can continue with my calculation. All right, recap. Clean up a little bit. Okay, as a recap, you have a population, and in that population there is a variable of interest. So variable of interest that is categorical, we call it x. X is categorical, and it's presence of something. And let's say you want to estimate the prevalence of someone with a certain gene factor. Okay, you want to know what is the proportion of people that have a certain gene factor. Okay, and in the population, that proportion is represented with pi. Remember, I told you before, some book they call it capital P, but we're sticking with pi. The way to figure out this is that you're going to get a sample. Let's say you got a sample of, oh, I don't know, 20 people, and you figured out that out of the 20 people, let's say 8 had the factor and 12 did not have the factor, and therefore that allows you to get an estimate, which is 8 to have it divided by 20, which is the total, and that's back to the 0.4. Okay, so this is my estimate of that proportion right here. Okay, now what I need to do is I need to calculate, let's say for the sake of the argument, I want to calculate a 90% confidence interval. The formula says you take your point as add and you subtract z, and then you multiply by the standard error, but this time you're going to use the estimate of this. That'll be p, so it's going to be p times 1 minus p, and you're going to divide by n. But before we continue, we need to check that we meet the requirement, which is n into p into 1 minus p. That has to be greater than or equal to 5. Okay, let's see what we got. Well, we know n is right there, so that's 20. You multiply that by p, we estimated p to be equal to 0.4, and then you multiply by the complement of 0.4, which is 0.6. Okay, that should give you, let me just do quickly on my calculator so that I don't get wrong values. Okay, so it's 20, and I'm multiplying by 0.4, and then I'm multiplying by 0.6, 4.8. Okay, so 4.8 is less than 5. In that specific example, I cannot continue, and I stop here. I mean, obviously there are other ways, there are other things you can do, but in this course, we're going to stop here. Okay, so let me change a little bit the settings so that hopefully I can be able to do it this time. So I'm going to change my sample size. Let's say instead of 20, I had now, let me take 40, and so I'm gonna take, keep things as they are. So now let's say I have 16 with 24, so that's 16 over 40, and I'm hoping that still gets you 0.4. Yeah, so everything remains the same except that now I'm multiplying here with 40 times 0.4 times 0.6. These did not change because I'm still having a 0.4 as my estimate of p, and so I'm just multiplying by 40 here, and I should get 9.6 this time, which is greater than 5. So now I can continue with my confidence interval. Okay, so what should I do? Let me clean up a little bit. All right. All right. All right, so my proportion is right there, so that's a 0.4 plus or minus z. What is the z value that is used when you need to do a 90% confidence interval? I hope by now you know it by heart. It's what's 1.6449, but in case you forgot, let me remind you that you go to your t-table, okay? And remember, we said in a t-table, first you have to find the area at the two-sided level, not the one-sided. So using the two-sided, you find the area, which is 90%, and then you're going to scroll all the way down to the Z, and here it is 1.6449. Okay, 1.6449. 1.6449, and then I multiply, let me do the square root of 0.4 times 0.6, and I divide by, remember my sample size is 40. Let's see what I get. I'm just going to run the calculation quick. So it's 0.6 times 0.4 divided by 40, and then you have to take the square root of the answer. All right, so when I multiplied these two together, I got and sorry, when I did the whole thing inside here, it was 0.006, and then when I did the square root of all of this, this whole thing became 0.07746. Notice I'm not rounding yet, it's too early to round here. Now I'm gonna multiply that by 1.6449 multiplied by the answer. That gets me 0.127. So this whole thing now, this entire thing is 0.1274. It means that I'm going to take my 40%. One time I'm going to add to it the 0.1274, and one time I'm going to subtract from it that value. So here we go. The lower limit is going to come out to be equal to 0.27. Now I can do a rounding, so I'm gonna do 2726, so I can say 273 as a round up, and 0.527. So this is my 90% confidence interval. The way we interpret this confidence interval, I can write up here, say, just we are 90% confident that the proportion of people with the gene factor, see, I take it back to what the question was about. It was the gene factor. So the proportion of the people with the gene factor in this population, I have to specify what population, is somewhere between the lower limit, so between 27.3% and the upper limit, which is 52.7%. Okay? This way I did my interpretation. Now, if let's say a certain organization comes to me, or a certain publishes a report that says if your country has a proportion that is, let's say, above 60%, then you qualify for a certain funding. Okay? So they say that if the proportion of this gene factor is above 60% in the population, we qualify to certain funding. Well, based on our results, if you come back to our results, what we are saying is that we think that this pie right here is somewhere between 27% and 52%. So the highest that we predict it will be is 52.7, and therefore the 60%, the cut point that they're suggesting, the cut point that allows us to get inside the funding acceptability, is not part of our interval, and therefore we do not qualify for this funding based on the results we're getting. We do not qualify. Okay? Whereas if for some reason another funding agency comes and say, well, we're willing to fund you if you're able to show that your pie is, let's say, for example, above 40%, for example, okay, or above 50%. Well, okay, now look at 50% and look at our interval. 50% is inside our interval. So 50% now is a possible value for us, and therefore we could, in theory, um, be able to submit for this type of a grant. Okay. Emma is you have another situation where funding, let's say, well, you're to be able to submit for funding, your pi has to be less than, let's say, 0.2 to be able to submit. Well, again here, if you look at the results we received, according to our results, um, نحن we don't think we fit the 0.2. نحن we think that the lowest this pi right there could be is 27% and the highest is 52. Now remember, when I say the lowest and the highest, it doesn't mean that the pi is changing value or it's fluctuating. Pi is a constant. The only thing is we do not know what the value of pi, but we're willing to say that we're 95% confident that it's somewhere between these lower limit value and upper limit value. And therefore, when somebody is suggesting a value less than 20%, we just have to say no, we do not fit in that suggestion. So any value between 27 and 52% is an acceptable value, and any value that is below the lower limit or above the upper limit is not an acceptable value. Okay, type. One last idea. What if you've done all this calculation? Okay, so we came up with our 90% confidence interval that says it's somewhere between 0.273 and 0.527. Okay. Now here's a question. What if we are asked to calculate a 95% confidence interval? What should happen? Okay, now remember, when you increase your confidence, when your confidence increases, what that is going to do is that the test you're using, the z-test in this example, is going to increase. And when the z-test increases, the width of your confidence is going to increase. Now, how does the width increase? Well, it means that the lower limit is going to move down and the upper limit is going to move up. Okay? And therefore, you expect the value for the lower limit to be lower than 0.2 and an upper limit that is upper than 0.527. Okay? Also, if you're asked to calculate a 99% confidence interval, then it's going to actually get even wider and wider. Think about it this way: if you try to draw your confidence interval on an x-axis, okay, so let's say that the confidence for the 90, this is the 90% confidence interval. Well, if you move into the 95, then 95 is going to look like this. It's wider. So this is the 95% confidence interval. And if you move into the 99, it's going to even get even wider and wider. Okay? Now notice how the lower limit gets smaller and smaller, and the upper limit gets larger and larger. And the opposite is true. If you started up with the 99% confidence interval and you want to move into the 90% confidence, then the upper limit has to move inwards and the lower limit has to move inwards as well. And I hope you notice that no matter how you're doing this calculation, always these limits are going to move into opposite direction. When the upper limit moves up, it's moving in this direction. The lower limit is moving in that direction, and they're moving in opposite directions. And when you're going to go from larger confidence to lower confidence, the upper limit is going to move downward, and the lower limit is going to move upward. And again, they're moving into opposite directions. Okay, so what does that mean? Well, it means that if you are provided with, let's say, the 95% confidence interval, if I say, well, this is a 95% confidence interval, and everything I said about the confidence interval, how the interval moves, applies even if you're doing a confidence interval for proportion or for the mean, or any kind of confidence interval. So let's say I'm saying that a confidence interval for an X bar here is the 95%, okay? It's between 140 and let's say 210, okay? And then you're provided a list of 3 confidence intervals. And so this is 120 and 300. And you have another one, which is, let's say, 150 and 330. And you have one more, which is, let's say, 160 and let's say this is 300. And the last one I'm going to write is this one, which is, let's say, 110 and 380. And let's say you're asked, out of these, pick which one is the actual 99% confidence interval. Well, remember when you're going from 95 to 99, the interval is going to get larger. So the lower one is going to go down and the upper one is going to go up. Let's see what is happening here. The lower one was 140, the upper one was 310. When you look at the first option we have, 140, so that it went to 120, went down. So that's a good lower one. But what happened to 310? Well, 310 also went down. So that's wrong because both limits of the interval moved in the same direction. 140 went down and 310 went down. So this is wrong no matter what. Forget about it. Let's look at the second one. What happened to 140? Well, 140 to reach 150, it went up, and 310 to reach 330 also went up. So both intervals went both limits went up, and that should never happen. So again, this is wrong no matter what. When intervals move in the same direction, it's a wrong answer. Let's look at the third one. What happened in the third one? Okay, so in the third option, 140 to reach the 160 went up, and the 300 to reach the 310, to reach the 300 went down. So this is the first time we have the two limits moving in opposite direction, which is good. That's a good thing. They're moving in opposite direction. But when they're moving in opposite direction and they're getting closer to each other, it means that the width is getting smaller. And that should happen when you lose on your confidence, not you gain on your confidence. Yani that should be, for example, a 90% confidence interval. Whereas the question is find the 99% confidence interval. So it's not the 99%. Let's look at the last one. What is happening in the last one? The 140 went down to 110, and the 310 went up to 380. So again, the limits moved into opposite direction, so that's a good thing. And the interval became wider, and that's exactly what we were hoping for. So that one down here appears to be the 99% confidence interval. Okay? Same idea applies for if I give you, let's say, 3 sets of confidence interval, and you have to tell me which one is the one that belongs when you change your sample size. Okay, so let's say you had a confidence interval, and this time I'm going to do let's say that's a 95% confidence interval for a proportion this time. And let's say the lower limit is 0.4 and the upper limit is 0.6. Okay, remember these are proportions, so it has to be 0 point something, and it has to be positive. And if I were to say, well, this was when sample size was 100, what will happen if I go to a sample size of 200? Okay, so what happens when you increase your sample size? Remember, when you increase your sample size, your standard error as a whole is going to decrease, and the width of the interval as a whole is going to decrease. So how would you decrease the width of this interval? The way to do that is that they have to get closer to one another. They have to move in separate direction, but they have to be closer. So the 0.4 has to increase. So now maybe it's 0.48, for example. And the 0.6 has to go down. So it becomes maybe 0.52, for example. Okay? That looks like a good answer for sample size 200. What about sample size of 50? So now I'm doing the opposite. I'm making the sample size going down. Your sample size gets smaller, your standard error gets bigger, and the width gets bigger. And therefore your whole interval has to get bigger. How does the whole interval gets bigger? The 0.4 is going to move down, and the 0.6 is going to move up. Okay, so this maybe becomes 0.31, for example, and the 0.6 may become 0.67. I don't know. I mean, I have to do calculations, but you get the idea. Okay? Then this sounds like a good confidence interval. Okay, I hope you find this session helpful.